thank you very much. It's a real pleasure to have the opportunity to present Quandela and what we do for our first Q2B. So myself, I'm Vale, Giesz, CEO and co-founder of Quandela.
I'm Niccolo Somaschi, CTO and chairman.
So first, let me introduce you what we do. So it's basically written. We build optical quantum computers, and recently we have plugged 2 computers in the cloud. But a few introduction about who are we. Quandela, it's a 5-year-old company, European company. Most of the team is based in Paris, actually, but we also have offices in Munich, Roma, and in Spain. And we have about 60 people dedicated to the development of optical quantum computing. So we have experts in semiconductors, in algorithms, in manipulations of photons with optics, and also in computer science.
There are different ways we can build up quantum computers. We can use matter-based qubit or photonic qubit. The matter-based qubits, they are objects that have a physical size and they take space on a chip or in a vacuum chamber, and they're very sensitive to the environment. And this is why we need to cool them at very low temperature or put them in ultra-high vacuum. The way we implement this qubit also constrain the way we can create entanglement with them. We can create it on demand, we can have 2-qubit gate efficiently, but both the noise, so the decoherence, the implements error, and the physical constraint limits their deployment and the large scalability, as well as the manufacturability. They have to be fabricated in millions, they have to be perfect, and they have to be interconnected. And today, there are no transducer to transform a quantum information in a matter qubit to a photonic qubit. On the photonic qubit side, photons don't sit on a processor, they fly through a processor, so we can manipulate them very efficiently with classical elements, with optical fiber, with telecom industry components and integrated circuits. But if we do this, if we use these classical elements to generate the qubit and to create entanglement, this comes with very low probability. And when we need to create a large entanglement with many qubits, with many photons, summing up probabilities forces the large increase of the resources, of the components that we need to deploy. In Quandela, we build photonic quantum computers taking the advantage of classical elements, optical fiber, integrated photonic circuit to manipulate them. But we use a matter qubit, a single photon generator, to create deterministically the qubit and to create the entanglement in a deterministic way. So these are semiconductor 3.5 nanocrystal. You can see there, they sit in a micrometer-sized optical cavity, and by controlling the monolayer of the structure very efficiently, these nanocrystals behave as artificial atoms. It means that they can create deterministically 1 photon per time, only 1 photon, and we can create directly entanglement in a deterministic way with the spin of the atom and the photon emitted. If we zoom out, the photonic quantum computer, the photonic quantum computer can be divided in this block. If you look at the hardware, we need efficient generation, efficient manipulation, and detection. Photonic qubits don't feel the environment, they don't feel the coherence, but they can be lost. So to reach fault tolerance regime, we need the photons to stay alive from the generation to the detection. It means that we have to generate them efficiently, the manipulator must be lossless, and the detection should be efficient as well. And the choice of the hardware, of the technologies we use, from superconducting nanowire detectors to photon integrated circuit and fibers, allow to reach this regime. And these are almost off-the-shelf components. On the generation side, the approach we take with the single qubit generator, deterministic generator, we can reach at the same time near unity and high qubit purity. And the value you see there, the 96% efficiency, is a theoretical value. You can find the references there. And the purity value, which is required to give high fidelity to the entanglement we generate afterwards, has been demonstrated by the founding team in back 2016. We start today deploying machines, and this is a video showing how it works. So you see there the qubit generator that stays at 4 Kelvin, is coupled to a fiber, and can generate photon up to gigahertz speed. And the photons then are demultiplexed and delayed with optical fiber and sent to large interferometer. You see there beam splitters and phase shifter. This is not bulk optics, it's just a representation of the integrated circuit. And by playing with the phase shifters and the way these photons interfere, we can reconstruct application and specific algorithm. So we detect them back at 4 Kelvin at very high rate, and the sampling and the output distribution gives rise to the results of the computation. On the longer term, the importance of having this artificial atom as a generator is that we can generate also cluster state directly from the single device. For scaling photonic quantum computer, we need measurement-based protocol, or INSPIRE, which requires generating offline large state of entangled photons, and then manipulate them with single qubit measurement. And the task of generating large cluster state can be done, as we've seen yesterday, either by linear optical components, not in an efficient way because it's probabilistic, forcing the deployment of thousands of components, or by using atoms, as presented in this paper. Atoms can be perfect generators, but they are slow, and the efficiency of extracting photon from the system is also slow. And what we have been shown already in this paper, you can see there, is that we can take the same device, the same footprint, and include a spin, and by spin photon entanglement, generating linear chain of entangled photon directly from this device. And we've been showing that we can do this with 2 and 3 photons, showing an improvement of 100% and 10 times improvement and 100 times improvement compared to other approaches. And this permits, of course, to reduce the overheads and pushes the scalability much faster. On the middle term, the way to improve this is to basically increase the coherence of the spin integrating in the structure. And we can do this. It's already been shown. We can push the spin coherence time up to tens of nanoseconds. And by doing so, because of the fast emission rate, we can squeeze in many photons and create linear cluster state up to tens of photons. And this is the main crucial hard block to scale up photonic quantum computer towards measurement-based application.
So now we have a first generation of computers based on the manipulation of single photons generated by our quantum dots in a cavity. So we have been working hard during years. The company is 5 years old, as I said, to integrate all the modules. We have a strong expertise by the founding team on the semiconductors, and then we have recruited many experts and engineers for developing the hardware modules that are allowed to scale up, to have reliable and viable use of the photons in these blue machines. On top of this, we have developed the compiler and the assembler to make sure that actually we can run some calculations on the hardware. So this is a unique way to run quantum computations because actually, as Niccolo explained, the photonic approach is very different from the matter qubit approach. And now, recently, we have finalized the front end on the end user interface, such that actually everybody in this room can connect and can use our machines. And now we have actually 2 QPU available on the cloud. So, in a few words, the main advantages of the photonic qubits is you can use semiconductor technology to emit and control and untangle qubits deterministically. And we can also measure the photons with a high fidelity and control them with photonic integrated circuits. And we use simple optical fibers to interconnect all this. So this is a very modular approach which is upgradable. If now you buy a Quandela machines, you will be able to change the modules and keep to have all the recent modules, such as actually your machine will be at the state of the art. This is a very modular approach, such as actually each time that you add a module, you will be able to double the performance of the machines. And by the fact that actually photons are chargeless, massless. They don't feel heat. We manipulate the quantum information at room temperature on classical devices, photonic integrated circuits at normal pressure. And this actually allows us to have a very low energy consumption, few kilowatts. And now the news, if it works, the remote. And now actually, Quandela has deployed these machines, the 2 QPUs in the cloud. So everybody can connect to cloud.quandela.com. And we have developed a very user-friendly interface, such actually you can have a company profile, you can have any interface. And this, on this interface, on the website, you can get access to 3 simulators, so noiseless simulators, noisy simulators. You can get access to the real QPU. Everybody in the room can connect, and you will receive free credits to run simulations and to run QPU. And then, in the long term, you will be able also to work with your team, with your colleagues, manage your projects, manage your tokens, and everything will be ready for scalability. And this is a very intuitive interface where our team of application engineers and scientists have written a very extensive documentations with many examples on how to solve real problems, real use case problems on our QPU. So for example, you can do variational quantum agent solvers or any well-known algorithms. And this is what I would like to talk to you now. Sorry. And just I mentioned a remark about why we believe that photonic qubits can be better than other qubits for machine learning applications. The fact is actually a photon, with photonic qubits, you can explore the Fock space. The Fock space is the space where you can have the 0, 1, 2, n photons that you can manipulate. And this, compared to the Hilbert space, a well-known qubit space with just a superposition of 0 and 1, here you can have the superposition of 0, 1, 2, 3, and more photons in one waveguide. And this actually is the size of the computational space offered by this Fock space is much, much, much larger than the Hilbert space. So when the Hilbert space is given by 2 to the power n, the Fock space, the size of the Fock space is given by this formula, where n is the number of photons and m the number of modes that you can have on our circuit. And basically, you cannot see clearly on this figure, but basically, if you consider that a machine with 10 photons, so 10 Fock particles, this is equivalent to about 20 Hilbert qubits. So we expect now, considering the fact that our simulators are limited to about 15, 20 photons for the strong simulations, we expect that when Quandela will be able to deploy QPU with more than 20, 24 qubits in the future, we will be able to provide our customers and our partners a real advantage for the simulations for their calculations, and especially in machine learning applications. So actually, these 24 QPU that we will have around 2024 will be equivalent to QPU with about 40 Hilbert qubits. With these first machines, we have been working with our customers, with our partners to explore industrial use cases. The first one is about cybersecurity, and Niccolo will tell you more about it just after. And also, we have been working on molecular design, for example, for chemistry, to develop new materials for drug discovery. And this is also, I will enter into the details. It's also possible to explore some logistic problems, as you can imagine. We have explored how to encode graph state, optimize graph states on a photonic processor. So if you're interested in these use cases, don't hesitate to contact us. And also can be very useful for time series forecasting, because actually we have seen that our processors can be very useful to predict and to measure the very weak signals in time series signals. So actually we have used our processor to generate entanglement and to generate quantum certified random numbers. We can solve nonlinear partial differential equations just by encoding the problems on our photonic circuits, and we can optimize logistic problems. So just to show you these figures, this is our first one of our first calculations of partial differential equations on real QPUs. So the lines and you can see the difference between the experiments and the theory that match well. So just to enter into the details, we have been working with EDF, French electricity provider in France, to solve partial differential equations. And basically here the main problem was how to predict, how to measure the propagation of cracks in hydroelectric dams. And actually our models, what we have developed with them, was very powerful in the sense that we have demonstrated some advantage with our photonic QPU by taking the advantage of these quantum properties of the photons. So actually we have deployed, and this is a publication that we will release, new techniques to have a better performance than classical supercomputers when we will have about 20 photons in our processors. The same with, for example, with NVIDIA, we have been working on how to train neural networks, considering that NVIDIA, our partners, had a database of polymers in their drawers, and they were wondering what will be the behaviors of new polymers that we cannot fabricate now, considering that we know how behave some other polymers. And actually, by using a good combination of hybrid classical neural networks and quantum neural networks, we have demonstrated that actually we can have a better training of our systems, such as we have a better classification of polymer molecules by using just a quantum layer on this system. And this is a publication that we released 2 weeks ago about the classification of polymers.
Just to focus now on the application in cybersecurity, have been mentioned in the past days by the largest player, Quantinuum, IBM, and so forth, that generating quantum random numbers certified is crucial for cybersecurity and especially post-quantum cryptography. And this is part of the work we have been doing with CryptoNext, which is world leader in the space. What we have been doing is to develop an application, a protocol that we call Entropy, that runs on a 2-qubit machine. And this allows to certify random numbers. And the way we do it is with the strongest certification possible we can take in nature, which is quantum mechanics, by leveraging Bell inequalities. And we like it also because it resonates with the news of the Nobel Prize Award early this month. It has been shown, in fact, that by violation of Bell inequality, you can use non-locality to generate quantum random numbers. But in this case, you need Alice and Bob to be separated by large space, hundreds of meters. And the way we solve this issue is by working and doing a proof of certification via non-contextuality in a CH violation. So we can squeeze Alice and Bob in an integrated photonic circuit and generate certified quantum random numbers in the standalone device that can be deployed on premise in non-laboratory environments. And this is the way we do it. We'll have a paper coming out in a few weeks if you want more details. So the take-home message is that we work strongly with scientific background, focus on the business, and this is a list of the publication of this year. 3 of them, they are submitted and under evaluation on the largest impact factor journal. And as well, that we already can deploy machines available on the cloud, work with customer for use cases that can run on simulators and the machine across all the sector, and that we have already the strong technical building blocks on the hardware with the cluster state generator, but also on the theory and the algorithm to scale up towards the error corrected regime. So this is Quandela. Thank you very much.
Thank you.
Okay, thank you to our speakers. Do we have time for maybe 1 or 2 questions?
Oh, thanks for your wonderful talk. I think you mentioned about differential equations, but could you explain a bit more about that and how good it is compared to classical computation algorithms?
Yes, we have developed a new technique where we use machine learning techniques involved by encoding the photonic circuit. I cannot tell you much more because our publication is going within a few weeks. But basically, if you want later, we can organize a demo and to show how it works. But basically, we do some minimization of cost function to solve and to find a solution to partial differential equations. For now, it's not better. But we have demonstrated, we see that when we will be able to have more than 20 photons in our circuits, we might maybe have an advantage here.